All right, it's 8 o'clock. Can everybody hear me and see the syllabus on the screen?
Yes, sir.
Yes, sir.
Great. All right, well, half of you guys are here, which is honestly more people than I had anticipated to show up, so that's wonderful. All right, so let's go over the syllabus. I'm me, Dr. Hartman, or Matt, I don't particularly care. Not that you have any access to it, but my office is in Nefkin Hall, room 211. My office hours are Monday from 10 to noon and Tuesday, Thursday, 1 to 5. Really, anytime, I'll be at my computer pretty much all day, every day. So just shoot me an email if you want to meet by Zoom, or if you want to converse by email, that's fine. I don't really care about the office hours so much. Email address, hartman@latech.edu. And then there's my office phone, which I'm actually will probably be around to answer this quarter, so whatever. Excuse me. All right, let's see. Special note, in the event that a disaster or other emergency results in campus closure, like the coronavirus, course will continue via Moodle. This is all online, so it's going to be Moodle the whole time. So blah, 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 log into Moodle and enroll in the emergency notification system thingy. Course objectives, we're going to expand our knowledge of circuits 1 and get into a little bit of the nitty gritty on amplifiers, RLC circuits, dive deeper into steady state sinusoidal circuits, and then work our way towards polyphase power. Excuse me. Textbook and reading materials. So officially it's engineering circuit analysis. Any circuits textbook will do. If you go into Google and Google the phrase CAD space ULABY, ULABY, there's a textbook called Circuit Analysis and Design by Fawad Ulabi, Michelle Maharbiz, and Cynthia First that's available for free from the authors. And I think it's quite a good textbook and it's free, so I would highly encourage you guys to download a copy of it. Let's see. I don't think the disability disclosure thing is probably going to apply, but you guys can read. Attendance, blah, 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 normal stuff. Academic misconduct, don't cheat, be less of a jerk than I am when we're good. Excuse me. Homework. So there's going to be homework problems posted on the Moodle page at the end of each lecture. Homework assignments are due within the first 5 minutes of class on the specified due date, must be properly formatted as detailed on the course's Moodle page. So we'll pop over and look at that in just a moment. Any homework assignment that does not adhere to the format detailed on the Moodle page will incur a penalty. Late homework assignments will incur a 25% penalty for each day they are late. So let's see if I can do this. And then how do I move this? There we go. That's not the right one. All right, so can you all see this PDF document that I've just opened up?
Yes, sir.
Yes,
Great.
sir.
All right, so I know I just realized I misspelled the word answer. That's pretty terrible. But here's how I want the homework formatted. So this is an old homework from last year. And so the assignment sheet, all of it is a cover page. So your first few pages or whatever, however many it winds up being, will be the assignment sheet just printed out as a PDF document or something like that. I don't think I gave you guys 6 problems this time. Then there is the handwritten work for homework number 1. Notice this is in proper engineering format, meaning I have my name, the class, the problem that I'm working on, page number up at the top. I have the problem statement rewritten. Excuse me. Then the solution begins. Go through all of my work. I boxed my answers. That +2 and +1 there just means that's how many points I assigned. Dang it, I don't know why I'm coughing so much this morning. So one thing that I want to point out here, I'm not going to do points for it or anything. It just annoys me. I hate fractions with a passion. So I would very much prefer if you don't do them. So like if I ask you to calculate something, that means that I want a numerical answer. I don't want an expression or anything like that, which that bugs the shit out of me on tests and things. Notice also I put 1.308 volts. So my expectation for you guys is, let's say I had something that was like 0.052 volts. I would not like that as an answer. I would prefer 52 millivolts. So I want your answers to be ranging from 1 to 999 of a correct unit. So I don't like, 0.6 amps should be written as 600 milliamps, things like that. Does that make sense?
Yes, sir.
Yes, sir.
So I'm not going to go through and just be like a complete jerk about it, but that is my preference. All right, so now that that's being said, part B, handwritten work, blah, 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 blah. Because I used MathCAD to do some of the work, the next thing that I have included here is my MathCAD work. So the expectation in this class is that we're going to be working problems, a lot of problems that are beyond the capabilities of the peasant calculators you used in Circuits 1. So you're expected to be able to use MathCAD. If you do not have MathCAD from leftover from when you took the Engineering 120 series, there's a link on the course's Moodle page to request access to it. Miss Ashley Osborne in the project-based learning office is handling all of those. Should be no big deal. Just submit the form and then she'll get you the info to install the latest version of MathCAD. I don't particularly care whether you use MathCAD 4, 5, or 15 because I have all of them. But if you send me a question with a MathCAD sheet, because you're asking questions about the homework problem, let me know which one you were using so that I can open it up in that one. That way I don't send you a response or help correct things in a format that you're not going to be able to open. Because that happened an awful lot last quarter and it was quite annoying. All right, so the gist of what I'm trying to get to here then is that there was all my, the cover sheet was the assignment sheet itself. Then there was the work for problem 1, the handwritten work for problem 1. Here is the computer work for problem 1 as well. Then here's problem 2. And the computer work for problem 2. And then next will be problem 3. And if I use the computer to do anything for problem 3, there that is. So that is the format that I am expecting. On several of your problems, I will ask you to use a program called LTspice to simulate the circuit. And we're going to use LTspice today just so I can kind of introduce you to it. But anyway, so does anybody have any questions about the homework formatting? All right, nobody's saying anything, so that's great. All right, so let's circle back around to the syllabus. Exams are all going to be open book and notes. Take-home tests, you'll have roughly a week to do them. And honestly, they're pretty much the same as a homework assignment as far as the formatting and all that kind of stuff goes, and the difficulty level, to be entirely honest. It's just going to cover a multitude of topics instead of one topic like each of the homework sets do. So the exams in this class, I feel, are pretty straightforward. You may wildly disagree, but that's okay. But nothing to particularly freak out about. All right, let's see. Grading, homeworks are 40% of your grade. Exams 1, 2, and 3 are each 20% of your grade. I don't curve, so anything above a 90 is an A, and 89.99 in my eyes is a B. Alrighty, then we have down here our list of topics and all that kind of good stuff where I've talked about the syllabus. I've made snarky comments, mentioned that you're going to be using MathCAD. So let's get into the circuit simulation portion. So if you could go to the introduction section on Moodle and take a couple of minutes and download LTspice, and then we'll meet back in say 5 or 10 minutes, and I'll walk you guys through setting up a circuit so that we can simulate it and get some results. Alrighty, do most of you guys have LTspice installed now?
Yes, sir. I got it.
All right, let me stop sharing this and then start sharing LTspice. All righty, so this is LTspice 17. It is a free circuit simulation tool. It is limited in its capabilities, but also very powerful. And we're going to be using it in this class an awful lot. So one thing that I want to point out here, and it is intentional, is that you can use this circuit simulation software, excuse me, to simulate, I believe, every circuit that we're going to deal with in this class, so that you have a means by which to check your answers if you can set up and run the simulation correctly. And that is very much intentional, okay? I don't use LTspice in Circuits 1 because all of the homework is done via web work, and so you could literally just simulate the circuit and get the answers and never learn how to do any circuit analysis whatsoever. Here in Circuits 2, I'm going to assume that since you have survived Circuits 1, you at least have some modicum of an idea of how to analyze a circuit. And so we're going to use these simulations as supplemental. We're going to be solving some complex problems And so this is a good way to check whether or not you're on the right path. So the first thing I'm going to do is go over here and open a new schematic, and it's going to bring up a gray screen with a fine grid that you, maybe I can't even see it either actually on this computer, doesn't matter. And so the circuit that I'm going to simulate is actually your first homework problem on the homework set that I've assigned as effectively a review of what I feel is important to understand from circuits 1 while we're moving forward. So it's problem 1, and it is a Thevenin Norton equivalent circuit problem. It's got, let's see, 1, 2, 3, 4, 5 resistors, 2 voltage sources, and a single current source. So for the resistors, up here on the top bar, there's a bunch of components. We can put down wires, we can put down a ground, label network, which we're going to be using extensively in this class. Then we have resistors, capacitors, inductors, diodes, and then a general component window, and we're going to be using that guy a lot too. But let's start with a couple of resistors. So I'm just going to attempt to draw as best I can the circuit, just laying out the resistors. So this resistor R1 that I've put down is going to be the 10 ohm resistor on the left-hand side. I'm going to rotate by pressing Control R so that I can put the other 10 ohm resistor down right around here. Let's come over here. This is going to be a 20 ohm resistor. This will be a 10 ohm resistor. Let me shrink my screen a little bit so I can see things better. And I'll drop the other resistors in a second. I'm going to start wiring things up or I'm going to confuse myself. So I'm using the wire tool and I'm just connecting the terminal of that resistor to this resistor. This is going to be my midpoint where I'm going to go up. Put in my other 20 ohm resistor. So let's go ahead and drop that guy in. All right, so I need a 20 volt source. So what I'm going to do for my 20 volt source is I'm going to click the component button, and it's going to bring up a menu. If I type in voltage, because I want a voltage source, it will give me one. And so I'm just going to drop that into our circuit, and it's going to break the wire and put it in exactly how I want it to do. Let's see, I'm going to need a current source as well. So I can just type in the word current. Notice that the current source is originally oriented as down. The direction of the current is down. In my diagram, in this circuit schematic on your assignment sheet, the current is directed up. So I'm going to rotate it twice to change the direction on it. Drop it over here. And let's see, I'm going to wire these guys up correctly. All right, so let's see, now I'm missing one resistor and a voltage source. That's not what I wanted. Alrighty, so from a component perspective, I believe I have everything in the right place and wired correctly. I know it might be hard for you guys to flip-flop back and forth between the circuit diagram and LTspice. I'm got multiple computers up here in front of me running so I can see all this. So now what I'm going to do is I'm going to assign component values, and let's start with these resistors. So to do that, I am going to move my cursor to the middle of the component and right click. And it allows me to put in the resistor value. So we have a 10 ohm resistor, so I literally just put the number 10. Notice there's also an opportunity to put the tolerance percentage so that we could, instead of having an ideal resistor, we could use this to simulate generic resistors within a specific tolerance band, and the power rating. So we could actually do some simulations that would see, all right, so what happens if I exceed the power rating and my resistor starts to decompose? We could do all of those type of simulations here inside of LTspice, but for right now, we're simply going to just put in 10 for the resistor value and then move along to the next one. This is also a 10 ohm resistor. This guy is a 20 ohm resistor. This guy is a 20 ohm resistor. 10 and 10. All right, so now let's mess around with these sources. So first I want to point out, intrinsically, the sources that we put when we get a voltage source are DC sources. And they are practical sources because they have both a DC value of voltage and a series resistance. We're going to come back to this in a second, but I'm going to click on this advanced tab just to show you what all of the different types of voltage sources we can actually get using this one simple component. So we can set up voltage pulses, sinusoidal excitation sources, exponential excitation sources. I don't remember what SFFM stands for. PWL file, so that means it's a piecewise function using linear segments. So effectively, we have a ton of different voltage sources at our disposal. This PWL and SFFM can be used for triangle waves and things like that. SFFM is better at triangle waves. PWL is just for generically odd-looking voltage signals that are just connected by smooth lines. All right, so we're going to go back to our DC bit. This is supposed to be a 20 volt source. This current source is supposed to be a 5 amp source. And this voltage source is supposed to be a 30 volt source. And another thing I'm going to do real quick is I'm just going to extend a line, a little stub here, and another little stub over here. And I'm going to use that label net command. I'm going to put VA on this one because this is going to be the nodal voltage at terminal A. And I'm going to put VB on the other stub. And that's the nodal voltage at terminal B. So how that helps me is, in part A of this problem, we're asked to determine the Thevenin voltage seen between terminals A and B of the circuit above by calculating the open circuit voltage of the live network with a positive polarity voltage reference on the left. So based on these nodal voltages VA and VB, what's my Thevenin voltage going to be? Like, not a numerical value, how am I going to mathematically evaluate it? Anybody have any idea what I'm talking about?
You'd have to use nodal.
Yeah, so I'm going to use nodal, but let's say that I've done nodal analysis and I know what the node voltages are. How am I going to find V Thevenin? So it's the open circuit voltage between terminals A and B with a positive polarity reference on the left. That's what I've defined in the problem statement. So what I'm trying to get you guys to say is that the Thevenin voltage is simply going to be VA minus VB. Does that make sense? Let's start there.
Yes, sir.
Okay.
Yes, sir.
So what I'm going to do is I'm going to simulate the circuit, and it's intentionally going to give me an error in a second. It's no big deal. We'll talk about why that error happens, and then I'll fix it, and then we'll be able to get our Thevenin voltage pretty easily. So the simulation that I'm going to run, I'm going to go up to where it says simulate in the ribbon, I guess, and I'm going to edit my simulation command. So we have lots of different options for the types of simulations that we can run. A transient analysis, which means we're going to be looking at waveforms as a function of time. Since this is a DC circuit, transient analysis is it's just going to give us straight lines. It's not going to give us values. It's going to give us a plot with constant values. So it's not super useful, although we can use it to determine the directions of things, and we'll get to that in a second. Then we have AC analysis. So this is actually a frequency domain analysis used a lot in designing filters and things like that, which we're going to be doing in this class. We have a DC sweep where we can change different parameters. So we can step up voltages or change resistances and things like that and see how the circuit behaves as we change the operating point of the system. We can do a noise analysis. We can do a DC small signal transfer function. This would be much more useful for course in transistor amplifiers. So we're not ever going to use this one actually. And then this last guy over here on the right is what's called a DC operating point simulation. And that's what we're going to use right here. Because it's just going to simulate the circuit as if it were a DC circuit, because it is, and tell us what the operating point of all of the different components are. So now that I have decided what type of simulation to use, if I click this little running man icon right here, it will run the simulation and it should give me an error. And the error that it's giving me, it says this circuit does not have a conduction path to ground. Please flag a node as ground. So the reason why it's important to have a ground in LTspice is because it uses nodal analysis to solve for everything. So that's going to make it a little bit harder to use to help make sure you set up meshes and things correctly, because it's more interested in finding the voltages with respect to ground than, say, the voltage drop over a particular component. Although it can find the currents through components very easily and all that kind of stuff, so we'll see. All right, so my next question to you guys is, where should I locate my ground? Anybody have any ideas or suggestions?
The very bottom.
Very bottom. Okay, so that is a reasonable place to put it. So what I'm going to do is I'm going to just put a little stub down. And the reason why I'm not directly connecting ground to that long horizontal wire is because sometimes in certain instances that makes the circuit simulation come out wonky. I can't figure out why it does that. So I always include a short stub of wire and then connect the ground. It's just to make life easier. All right, so move some of this Zoom stuff out of the way. All right, so now I'm going to run my simulation again, and it just gives me a list of things. So up here, it says V, open parentheses, VA, close parentheses, and a colon. So the nodal voltage at node VA is 32.5 volts, and the nodal voltage at node 3, which we're not exactly sure where that is right now, but we can figure out in a second, is 30. The nodal voltage at node 1 is 35. The nodal voltage at node B is 12.5. The nodal voltage at node 2 is 32.5. And then it tells me the current flowing through all of my elements, but no direction is indicated. So this is one of the limitations of LTspice. So if we close this, well, first, let's figure out what the Thevenin voltage is. So I said earlier that it should be VA minus VB. So 32.5 minus 12.5 means the Thevenin voltage should be 20 volts based on this analysis. Everybody okay with that?
Yes, sir.
Yes, sir.
Okay, great. So when we mouse over particular nodes, if you look in the bottom left-hand corner of your LTspice screen, it says this is node, so where I have my mouse right now, this is node VA. The DC operating point is 32.5 volts. So once we run that simulation, it actually stores all that kind of stuff. So we can mouse over this guy, and it tells us that the DC operating point for this resistor is 250 milliamps. So whenever we mouse over a node point, it gives us the nodal voltage. Whenever we mouse over a component, it gives us the amount of current that's flowing through that component. It also tells us that the dissipation is 625 milliwatts. That means that this resistor that is labeled as R1 is absorbing 625 milliwatts of power. If we mouse down here and put our cursor over the 30 volt source, we can see that it has a current of 250 milliamps flowing through it, and its dissipation is 7.5 watts. So that leads me to believe it is absorbing 7.5 watts. This guy is dissipating negative 175 watts, so it's supplying. This guy is dissipating positive 2.5 watts, so it is absorbing. So this current source is actually doing the bulk of supplying the power to the circuit. But one thing that we can't really see is the direction of any of the currents or anything like that, and that can be troublesome. So how we can alleviate that is I'm going to delete my DC operating point simulation, and instead I'm going to run a transient simulation, and I'm going to stop it after 1 second. So if I run this transient simulation, I'm going to make this fit. So it's given me a completely blank plot on the top half of my screen, and it's because I haven't told it what I want to see plotted. So I want to mention a couple of things. When we're doing a transit simulation and you mouse over the schematic, if you move your cursor over a node, this is a voltage probe, okay? So it's going to give you the nodal voltage, and it plots it as a function of time. Since this is a DC circuit, we're seeing that it's 32.5 volts for all values of time that we've mapped it. If instead I move my cursor over a component, so no longer over a node, this is a current probe. And notice that there's a red arrow and that arrow has a direction. That is the direction that the current is flowing, okay? So when we make that measurement. So in this case, when we make this measurement, we'll see that the current flowing down through that R1 resistor is 250 milliamps. The current, because I rotated my current source twice, this current probe is giving me the direction up. But let's say, just for argument's sake, that I wanted the current flowing up through the resistor R1. What I can do is, if I right click on my plot, I can add a trace. And I have all of these different things available, all of these different variables. So what I'm going to do is, because I want the current flowing through resistor R1 that is in the opposite direction, I'm going to put negative and then click on IR1. And now it gives me the opposite current. Does that make sense to everybody?
Yes, okay.
Yes.
Okay, so what's really interesting about that ability, and we'll use it an awful lot when we get into our RLC circuits, is that the expressions that I add don't necessarily have to have anything to do with any of these variables that are stored in my simulation. So I could work out an analytic solution to, say, an RL circuit. Actually, let's do that real quick. So let's close these out. You guys have seen how to do a simple DC operating point simulation to check something. No. All right, so let's say that I have a simple RL circuit. I'm not even going to put a source in there, and we'll talk about why in just a moment. All right, so let's say that this should be 10 ohms, and this will be 2 henries. I'm going to put my ground down here. Now, if I simulated this circuit right now, it's going to give me literally nothing because I haven't told the program that there's any initial current or anything flowing through the inductor. So how I'm going to do that is I'm going to click on this button that says .op, and this is a SPICE directive. And I'm going to do .ic, that's for initial condition, I, L1. So the initial condition on the current flowing through my inductor is going to be 5 amps. Okay, so based on what we know about an RL circuit from Circuits 1, and this is a source-free problem, which means we should be dealing with the natural response of our RL circuit. We know that the natural response will be the initial condition on the inductor current multiplied by E to the negative R over L times time. Does anybody recall that?
Yes, sir.
Great. Okay. So, Cord, I think you're probably just amusing me, not amusing me, but placating me at this point, but that's perfectly fine. So let's
It
see.
sounds familiar.
Okay, that's good. That's very good news that it sounded at least familiar. So I'm gonna, let's see, it's gonna decay. It's got a time constant of 2/5 of a second. So I'm gonna let it run for 1 second. That'll be roughly 5 time constant. Actually, let's let it run for 2 seconds. So we should see it decay pretty much all the way down to 0. So I'm gonna run my simulation. And I'm looking at the current through the inductor. So it starts at 5 and it decays down to 0 in roughly a little over between 1 and 1.2 seconds, which is exactly what I expected. So my mathematical model, I can check to see if that is correct by adding a trace and then typing in the expression. So what I said a moment ago is that I should observe that it is the initial value, which is 5, times an exponential function, where that is going to be, let's see, negative R over L. So that's negative 10 over 2, which is negative 5 times T. And here, we can't do T, so we have to actually explicitly say time. So this is my mathematical model that I have developed by understanding how RL circuits work. Press OK and add it, and notice that those two lines exactly cover each other up. So what does that mean? Anybody got any guess?
Means they're the same thing.
They're the exact same thing, exactly right. So my mathematical model that I've developed using my circuit analysis techniques matches my simulation. So that is a very good indicator that I have solved this problem correctly, okay? So there's a couple of transient analysis problems on your first homework assignment. That's a review. We're gonna get into second order circuits in this class, and to do that, I need you guys to remember how to work with first order circuits like the one we've just handled. So this is a very, very good way for you guys to make sure that you're approaching these problems correctly. You could do a DC operating point analysis on the original circuit to figure out what's going on at t is equal to 0 minus, and then use the initial conditions that you develop there to analyze the circuit in its, so this would be valid for, say, t is greater than or equal to 0 plus. This is what we have shown for this particular circuit. So a DC operating point simulation, which is what we did a little while ago, would be good for figuring out what's happening at t is equal to 0 minus. And then this transient analysis tells us what's going on for all other points in time. So we've used LTspice a couple of different ways. Anybody have any particular questions? I know it's going to take a lot of practice for you guys to get familiar with doing all this kind of stuff. So I encourage you, even if I don't specifically ask you to use it on a problem, you know, try things out and just use it to check your answers and get used to running simulations. All right, so does anybody have any questions or anything right now? Nobody's saying anything. Okay, so that's pretty much what I've got prepared for today. So what's going to happen for Monday's lecture? is I'm going to prepare some material and record it this weekend. I hope to have it up. Actually, hopefully I'll have it up tomorrow. My expectation is that you guys will watch the video and then come to class on Monday at 8 a.m. or whenever the hell it is we're supposed to meet, because some of my classes meet on different times on different days. I think this one is 8 o'clock Monday, Tuesday, Thursday. Anyway, so you'll come to the Zoom meeting on Monday. And if you have any questions, I'd be happy to answer them. And if you don't have any questions, then we're just going to work some problems that will help kind of solidify the lecture material. And that may involve actually doing what we did today, where we, worked a portion of a homework problem or things like that. So that's going to be the layout of the class from here on out. I'll have pre-prepared materials for you guys to view in advance, and then the class times will be used to answer any questions that you may have, and then work on numerical examples and things like that to kind of reinforce the theory. Everybody, does that sound groovy?
Yes, sir.
Okay. All right. Well, believe that's enough out of me. So we covered the syllabus. We've used LTspice. We talked about MathCAD. Yeah, there's a homework assignment that's already uploaded on Moodle, so you guys can start working on that. If you need a refresher on how to solve for Thevenin and Norton equivalent circuits, how to do transient analysis, or how to analyze an op-amp circuit, I can give you guys a link to my YouTube channel where I have videos on all of that stuff from teaching Circuits 1 last quarter. So I'll throw that link up on Moodle, and then you guys should be good to go for your first homework assignment. The first homework assignment is due 1 week from today. So unless anybody has anything else to say, we are done for today's lecture or whatever. All right, nobody's saying anything, so I'll catch you guys on Monday. Have a good weekend.
Have a good
Take care.
weekend.